right, so let's get to talk about queues. The queue operations here is another abstract data type. So when you talk about queues now, they're a little bit different from stacks. When you talked about stacks, we talked about them using the last in, first out kind of logic. But when I'm talking about queues now, they use the first in, first out kind of a logic. So whenever you think about queues, you can just think about a queue that we always find probably in banks, the queues that will be probably at bus stations or at train stations. The first person to get on the queue is the first person to leave the queue, basically. So we are saying that queues are going to be using the logic of first in, first out. That's FIFO, yeah? So we're going to be implementing a queue using an array as well. So suppose that we have in our array that has got 7 elements, that can take 7 elements starting from index position number 1 up to index position number 7, and we are naming our array a queue. We are going to be having 2 pointers. Before we even talk about the part of the pointers, you need to know that queues can be implemented as linear queues. These are basic queues. Then we also have the implementation of queues coming through to be secular. So we have linear queues and secular queues. So I will just start by the basic linear queues with this example. Then I will talk about secular queues, which we are going to be implementing in code. Same again with linear queues, we're going to be implementing them in code, but they're pretty basic. I think you can do this by your own, and I will just help you with the implementation of secular queues. So what you're saying is this. If we're talking about linear queues right now, we have our array that is called a queue, a 1D array that is called queue, that has elements starting from position number 1 up to position number 7. So by this time, I'm pretty sure that you now already know how to declare this array. It's an array that consists of 7 elements. I'm just going to be having it like it's empty for the meantime. So it's an array that is called queue that contains 7 elements. So to create that, we're just going to be saying declare. The name of the array is called queue. So I'm going to be having it like this. Queue, then we indicate that that's an array that is consisting elements from position number 1 up to position number 7, the lower bound and the upper bound. Then in this case, it's going to be holding values that are integers. So I'll be like of integers like this. That's how I will declare my array in pseudocode, yeah, of integer. So that's how I'm going to be creating my array. So now I'm seeing that the other thing that you're supposed to be knowing is that whenever we're talking about queues, they're supposed to be coming through with 2 pointers. One pointer to point the element that is at the front, to point the index position of the front of the queue. So front pointer points the front index position. Then the rear pointer points the index position that is holding the last added element. So this points the index position, index of the front of the queue, right? So in this case, the element that is going to be sitting on the front of the queue will be sitting on position number 1, right? But when we talk about rear pointer now, it's pointing on the index position, is the index of the last added element, the last added element. So in this instance here, the last added element was sitting on position number 4. So my rear pointer will be 4 because it's the index position of the last added element. The front pointer will be always 1 in this case. When the array is empty, when the queue is empty. So the front pointer will be 1, indicating the index position of the front of the queue, right? So I'm going to declare these elements with as simple as this. These are going to be holding integers, so I'm just going to be creating the front pointer, that's FP for me. Then I create again the rear pointer, that's RP for me, as what? These are going to be coming through as integers, right? So if the kill is empty, then my front pointer is going to be given a value of what? If the kill is empty, the front pointer will be 1, but the rear pointer now will be 0, to indicate that there is no element yet in the array, right? In the kill, I mean to say. So the rear pointer will be 0, pointing at nothing, because there is nothing that has been added. But if we go ahead now, and if we want now to increment, right? If we now want to increment an element into a queue, so this is the basic part as far as declaring a queue is concerned. This is how we declare, this is how we create or we initialize a queue. Initialize a queue. We just have to mention that we have a queue that is called a queue. We or you can just, let's just call it my queue, so that it differentiates. My queue is the variable that is the identifier for the queue that I just created. So my queue is an array that contains elements from 1 to 7. Then we have fp as the front pointer, we have rp as the rear pointer, and they are initialized to 1. Front pointer is initialized to 1, indicating the index position of the front of the queue. Then the rear pointer is initialized as 0, indicating that there is nothing that is in the queue as yet, because the rear pointer, it is the index of the last added element. So when we want to add elements into a queue, we enqueue. We use the function enqueue like this. If we want to remove, we enqueue, then we take in the element that we want to add, right? Then when you want to remove an element from a queue, we use the keyword, the function that is called dequeue. So dequeue, it just removes an element from a queue. And the element that is dequeued is the element that is on the front pointer. Because remember, we said whenever we are we're removing an element, we are removing the element that is the first to be added into the queue, yeah? So there are a couple of principles that you need to be, a couple of stages that you need to be following whenever you are enqueuing. Let's start by dequeuing, right? Whenever you want to dequeue, whenever you want to remove an element from a queue, you first need to check if there is an element to be removed. You get the point? You first check if the queue is not empty. So in this instance, the queue is going to be empty if my RP is 0. If my rear pointer is 0, then there is nothing to remove from the queue. So you first check if RP is not 0. So if RP is not 0, then there is definitely something in the queue, because my rear pointer indicates the index position of the last added element. So if the rear pointer is 0, it means that nothing has been added in the queue. So first check if the queue is not empty. That's the first thing that you need to do, yeah? Then, if not empty, you go ahead now and remove the element that is on the front pointer, right? You remove the element at the front pointer. So if you remove the element that is on the front pointer, which is 27, in this case, 27 will be removed. So my front pointer is no longer 1. My front pointer now is going to be indicating the element that is sitting on the following index position. Why? Because 27 has been dealt with. So when I remove 27, I may need to replace that with empty, right? Replace the index fp with empty. So they removed 27 here, and they replaced empty on that index position. Then the step number 4 that they then did now is the part of incrementing a front pointer. So the front pointer was 1, now it's 2, to indicate the following next, or the following first. You get the point? So if the first person was on the queue is null in the bus, the new first null is the element that is sitting on position number 2. So we are saying that we now increment the fp to indicate that we now have a new front pointer. We are doing nothing as far as the rear pointer is concerned. The rear pointer is indicating the index of the last added element, which is still 4, but we have incremented the value of front pointer to indicate that we now have a new free. These are the steps that you're going to be taking. So else to this now, we say that the first thing is to check if the queue is not empty. So if it is not empty, you go ahead and do these things. But else, which means if it is empty, you just output an error message, right? You output an error message that the queue is already what? is already empty. You output an error message. That's basically what you do as far as queues are concerned, as far as the dequeue part is concerned. So kill after dequeue, 27 is going to be removed, and 27 has been removed, and the where 27 was is been placed with an empty, and the front pointer was incremented by 2. It was incremented by 1, I mean to say, to indicate that the front pointer is now what is sitting in position number 2. You get the point? So that's basically what our dequeue is going to be working. We are still talking about a linear queue, remember. But if we are talking now about the part of enqueuing now, we are adding an element at the end of the list of the queue, I mean to say. So we are adding an element. So it means we need to take an element first whenever we are enqueuing. Enqueuing, you need to take an element that you need to add into the what? Into the queue. So the first thing that you need to check is, isn't my queue already full? First, you check if the queue is full or not. In this case, the queue is going to be full if my rear pointer is already 7. You get the point? If my rear pointer is 7, then there is no way that I can add an element. Remember, we're talking about a linear queue. The last element is supposed to be sitting on position number 7. So if the rear pointer is already pointing on number 7, then there is no space to add an element for a linear queue. So we're going ahead to say what? We're going ahead to say that number 1, we check if the queue is not full already, right? So if the queue is not full, what I'm going to be doing first is I'm going first to increment the value of the rear pointer. Right now my rear pointer is pointing at number 4, which was the index position of the last added element. So for me to place something, I need to place it on position number 5, which is the next pointer, which is next to the rear pointer. So first of all, I need to increment the rear pointer. Increment the rear pointer by 1. So if I say rear pointer plus 1, I'm now pointing at number 5. My rear pointer now is now what? Is now 5. Then I now go ahead and place the element on position rear pointer now. So you place the element, this element that you just took here, the element on the rear pointer now, position number 5. And that's going to be pretty simple. You're just going to be saying my queue, right? My queue position of rear pointer is the one that's going to be getting the element. That's the code that you're going to be using that, right? So you place the element on rear pointer. That's basically what you do. After you do that, now you are done basically. That's all that you need to do. You take the element, you just increment rear pointer to point on the next free position. You go ahead and place the element on that rear pointer. That's all that you need to do. So are you seeing something here? The rear pointer is changing each time that I'm enqueuing, but nothing is happening with the front pointer when I'm enqueuing. So enqueuing affects only the rear pointer, but dequeuing affects only the front pointer here. The front pointer is what that's going to be changing because it's supposed to be pointing now on the next front. So we affect the front pointer when we are dequeuing. We affect the rear pointer when we are enqueuing. That's basically it. So here, else to this now, we said we check if the queue is not full. So if it is not full, we go ahead and do this. But if it is full, we output again an error message, right? An error message. That's the one that you want to be outputting. That's basically how linear queues work. They're pretty simple, pretty basic like that. So I would appreciate if you go ahead and probably try to write the code by yourself. Then you can share with me how the complete pseudocode is going to be looking like with the explanations that I just gave you. That would be more than just wonderful. Okay, but my key part now is not really on linear queues because they are pretty basic the way that I just explained them, straightforward. The real fun part is going to be starting when we start to talk about the part on secular queues. Check this part now. When we talk about secular queues now, secular queues, they work with the notion that if an element has been removed, then that position is now free or ready to be populated. You get the point? So I can give probably an example that's going to be sitting like this. like here, if it's a linear queue, right? Whenever we remove, right here we have just removed the queued 27. So this is now free to be populated. So if my rear pointer is now 7, suppose that I have added 31 here, 24 here, and 30 here, I'm still supposed to be able to know that there is still some space to add an element. You get the point? Which is here. Linear queues do not allow that. Linear queues, they just say that the last position is 7, so which means if 7 is populated, then the queue is full. But circular queues are saying that whenever we remove an element here, this becomes a new free point that can actually be given some new values. So we can even go ahead and populate another value, which is probably 20. And 20, this becomes now my new rear pointer, and this being the front. So the front is on position number 2, but the rear is on position number 1, which makes sense, yeah? Which makes sense because we are saying that the first person to get into the queue was 27, but 27 then got into the bus, which means the new first was now 37. All the other people who then came are supposed to be behind 34, which makes literal sense or even technical sense because literally the first person to get into the queue now was 34 and is the one that's supposed to be on the front, and 20 was the last to come in and should be sitting on the on the last position. That's basically how linear queues are going to be working. So check this out now. We're coming through to appreciate that at any given instance we might have the case whereby we might have the rear pointer being equal to 3, meaning to say that 19 was the last added element into the queue. But the first element that was added into the queue is on position number 10. So the front pointer is 10, but the rear pointer is 3. You get the point? In this instance now, when you're working now with circular queues, there's some added attributes that we need to be working with now. We need, again, to know the queue length at any given point in time because index positions are not carrying it. We need to know the queue length at any given point in time. So in this time, so when the queue is empty, which means the queue length is 0, right? When the queue is empty, the queue length is going to be 0. Then we go ahead and actually have, again, the upper bound. The upper bound is the highest index position where data upper bound is going to be the highest index position. The highest index position here is 10. So in this case, it's going to be 10. If this is my queue, in Python, this index will be 0, and this will be index number 9. So the upper bound, just know that part that it's the highest index position. We need to keep track of this so that we know what will be the value of our rear pointer at any given point in time. Yeah. Then we need also to know we said we need to know the queue length, which is the number of elements that are in the queue. We need to know the upper bound, which is the value of the highest index position in this sense. So it can be 9. If the queue is holding 10 elements, then in Python the highest index position. This is okay. Let me just put this part. So the upper bound is the highest index position, and this is going to become index position. Yeah, it's different now with the number of number of elements. Queue length is the number of elements. So number of elements or queue length is 0 if the array is full, but the upper bound is always going to be equal to 10 using this example. Yeah. Then you will see that again we need also to play part with to have the value of a full element. Of a full queue, I mean to say, if my queue is full, it's supposed to be holding 10 elements. So this is coming through to be a little bit different. That's the reason why I'm actually having these two variables different. Full queue is going to be having 10 elements. Then my upper bound is goes to 10. This is going to be different a little bit when you're talking about Python because the upper bound will be 9 because it's an index position, but the full queue is going to be still 10. Always master that part. Then, of course, we will need the rear pointer. Of course, we will need the front pointer. If the queue is empty, the rear pointer is going to be, in this case, my rear pointer is going to be 0. Then my front pointer will still be 1 when the queue is empty. Right? So these are the number of elements, the number of attributes that I'm going to be using. 1, I need the number of elements. 2, I need to know again the upper bound. 3, I need to know the value of a full queue. Then I need also to know the value of the rear pointer at any given point in time. 5, I need also to know the value of the front pointer. So these are the attributes that I'm going to be using when I am dealing with a linear with a circular cube. Just about a minute. Not really. When I am dealing with a linked list. Sorry, when I'm dealing with a circular queue, I need to make sure that I have the number of elements, the upper bound, the value of the full queue, and the rear pointer and the front pointer. So I need to know exactly what's happening with these attributes. You see that the number of elements is going to be changing. So this is a variable. The upper bound, this never changes. The upper bound is going to be a constant. The full queue again is going to be a constant because the number of elements that are supposed to be in the queue never changes. Then the rear pointer always changes. The front pointer will always change again. So the rear pointer will change, as we talked before. The rear pointer will change after enqueuing. Yeah. Then the front pointer will change after dequeuing. Right? Then the number of elements will change in either way. Even if we dequeue, the number of elements changes. If we enqueue, the number of elements also changes. So just know that these attributes are always supposed to be changing each time that I add an element. Let's talk about it now in a GUI state. If I add an element here, I'm going to be having my rear pointer added to actually come through to be this. So let's say I add 40. If I add 60, rear pointer changes first, 41. If I add another element, rear pointer changes 60. Add another element, rear pointer changes 90. Another element, rear pointer changes 100. Another element, rear pointer changes is 70. In this case now, my number of elements is now 10 and my full queue is already 10. So at the very end of the day, I cannot add another element. If I hit dequeue now, check this part. If I hit dequeue, I'm going to be removing 23. If I remove 23, then my new front pointer, simply because my front pointer was equal to the upper bound. My front pointer, if my front pointer is equal to the upper bound, then my new free pointer is now going to be coming back to 0. To 1, I mean to say. So that's one thing that I need to be checking. When I dequeue, I need to check now what was the value of my front pointer. If my front pointer was less than the upper bound, then I can just go ahead and increment the front pointer to have the next front pointer like what you did before. But if my front pointer was equal to the upper bound, I don't have to add 1, because if I add 1, I'm going to be going to 11. So I need to come back here now. So if my front pointer was equal to the upper bound, then my front pointer is going to be changing now to 0 after dequeuing. I hope that makes sense. Then again, my rear pointer again, whenever I want to enqueue, as long as my rear pointer is still less than the number of, as long as I still have space in the array. Okay, let me let you check on this. As long as I still have space in the array, I can actually add my rear pointer. I'm not adding an element because my rear pointer is less than the upper bound. You get the point? That's not the thing that I'm using to check. I'm adding an element because the number of elements is still less than, the number of elements here is still less than the full queue. So I can add an element to that. So check this out now. Let me just go ahead and actually show you the pseudocode that they have here. Okay, let me just clear this. I need to clear a section. Let me just take an eraser for this. Okay, cool. I'll maintain those attributes on that corner so that I can erase this. Right, check this out. to create a queue, the basic things that I needed to do were initializing a queue, right? This is a circular queue now. First of all, I create my queue that holds 10 elements. I create my rear pointer, I create my front pointer, I create my full queue, which is an integer, and I create the number of elements, which is the queue length. Yeah. What did they not give me here? The upper bound, yeah? They did not give me the upper bound, but rather, let's just assume that the upper bound is there. Then they're telling us that the front pointer is 1. We talked about this, which is okay. Then the end pointer, this was supposed to be the rear pointer, yeah? The rear pointer, the one that they created here, is 0 because there's nothing yet. Upper bound is 10. They just gave me this as a constant here. Then the and I have my FP, I have my RP, I have my upper bound, which is the highest index position, which is 10. The full queue, I have it, which is 10. Then my queue length is 0 because this is an empty. This is an empty circular queue, right? Empty circular queue, right? I hope that part was clear enough. So with that having been said, they went on now. Let me just erase this because we need to talk about the other part now of enqueuing. Okay. So if we are now enqueuing now, it means that we are now adding an element into the queue. Yeah. If you're adding an element into the queue, first of all, you check if the queue, the number of elements that are in the queue are not full. So you're checking first if the number of elements in the queue are still less than my full queue. If the number of elements that are in the queue are still less than 10, then I can add something into the queue, which makes sense, right? Otherwise, we're just going to be saying that the queue is full, right? We cannot add anything. Then we now need to check again if the rear pointer is still less than the upper bound. If the rear pointer is still less than the upper bound, that's pretty much simple. We just go ahead and increment the rear pointer. Because we are trying to avoid the part where we need to add the rear pointer if the empty space is this one, yet the rear pointer is this one. Yet here there is an element, whenever there is again an element. So if we want to add an element in this instance, just adding 1 to the rear pointer is going to be giving us something that is now out of bound. 1, 2, 3. It's going to be pointing now to 4, of which 4 is not part of this. So we need, if the rear pointer is still less than the upper bound in this case is 3. If it's still less than, suppose the rear pointer is 2, then we can go ahead and actually add the rear pointer. We can just add 1. But if the rear pointer now is equal to the upper bound, then we need to go ahead and actually have the rear pointer now point into this. Make sense? Because we're enqueuing the rear pointer, suppose we're pointing now to 1. Why did we do this? Because we already know that there is a space that we can actually add an element, but we don't know where it is. So the space, if the rear pointer is still not yet the upper bound, we just add 1. But if it is null equal to the upper bound, then we just go ahead and actually take the upper bound, the rear pointer to be equal to 1. So that's what they just did here. If the rear pointer is equal to upper bound, we go ahead and actually make the rear pointer 1. But if the rear pointer is still less than the upper bound, we go ahead and actually increment 1 to the upper point, to the rear pointer to indicate where we are going to be adding an element. From there, we go ahead and increment the number of elements that are null in the queue, and we place the item on the position of the rear pointer. Pretty simple, right? So try to put this in Python. But just understand this logic again in pseudocode, because that's going to be asked in paper 2. So with that having been said, the last part that we have is the part of adding an element. So you see, enqueuing, with removing an element, I mean to say, enqueuing, he had to have us what? He had to have us, enqueuing, he had to have us removing a what? He had to have us adding an element and changing the value of the rear pointer. Check the part now as far as dequeuing is concerned. If you want to remove an element, we first check if the length of the queue is not 0. Because if it's 0, it means that there is nothing that is in the queue, yeah? So if the length is 0, then we just go ahead and say that we cannot dequeue anything because there is nothing in the queue. Otherwise now, the item that we want to dequeue is the one that is sitting on the front pointer, right? That is already known. We remove an element that it was the first into the queue. Then check this part now. The value of the front pointer is going to be changing based on the part that if the front pointer was already equal to the upper bound, like what we had here, I think I explained it here. If the front pointer is already equal to the upper bound, the front pointer now becomes 1. You get the point? Otherwise, if the front pointer was not equal to the upper bound, the front pointer now becomes 2. You get the point? We just add 1 if the front pointer is not equal to the upper bound. So the first thing that you need to be checking is that is the front pointer equal to the upper bound, yes or no? So if it is equal to the upper bound, then the front pointer changes to be the first index position. But if the front pointer was less than the upper bound, then we just go ahead and increment the front pointer to have the new front pointer. That's basically what we're talking about. So I'm saying here, this is it. If the front pointer is equal to the upper bound, we just have to make sure that we come back to the very first element that is to the very first index position to indicate as our front pointer. But otherwise, if the front pointer was less than the upper bound, we go ahead and just increment the front pointer, and we decrement the number of elements that are in the queue. These are the things that you're supposed to be knowing. So this is the index. This is how we're going to be putting this queues in their pseudocode state. I hope that was quite understandable. So with that now, I might need to show you again the Python code as far as this is concerned. The Python code for this is this. For a circular queue, let me just clear everything that is on the screen. Beautiful. This is the circular queue implementation. So for this reason, I just had probably, let's just have 10 elements then. Okay, let's just have 4 elements. So if my linked list, if my circular queue, I don't know why I'm thinking about linked list. If my circular queue is going to be coming through with, let's say 4 elements. So an empty circular queue, let me just call it my queue like that. Yeah. If an empty my queue with 4 elements is going to be having none times 4. Why none times 4? It's indicating that I have 4 empty spaces. Check this out. If I just say A is equals to none times 4 like that. It's just, if I then print A, it's going to be telling me that there is none, 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 none. And none just means that it's an empty space. You get it? So we are saying that we have 4 empty spaces here in this my queue. My front pointer is 0. As I said, in Python, it's not 1. Every index position starts from position number 1 in Python. So from position number 0. So my index position of the front pointer is 0. Then my rear pointer is -1 to indicate that there is nothing yet in the queue. Then my upper bound is 3. The index position number 3 is going to be my upper index position. Then the queue length is 0 because there's nothing yet, but the full queue is going to be having 4 elements. So if I want to add an element into the queue, I need to be using the global queue. I need also to be using the global rear pointer, because these elements that are here, they are global elements. They're supposed to be changing each time that I affect them inside the function. So my function and queue takes an element as a parameter. I go ahead and take the queue here, the queue length here, and the rear pointer that is here. I just make them global here. Then, if my queue length is still less than the full queue, it means that I have some way that I can add an element. Then I go ahead and check the value of the rear pointer. If my rear pointer was still less than the upper bound, I just increment the rear pointer. So this logic is just the same as rear pointer is equals to rear pointer plus 1. It's just the same thing. Rear pointer plus 1 is just the same logic. Then otherwise, if it is not less than that, it means that the rear pointer is equal to the upper bound. If the rear pointer is equal to the upper bound, I just go ahead and increment the upper bound to be 0. Then I place my element on the rear pointer, then I go ahead and increment again the queue length. So this is the same as even saying queue length is equals to queue length plus 1. Then I return the value of true to indicate that I have added an element. Then else to this, if my queue length is not less than the full queue, which means that it's equal to the full queue, then it means that I need to print the value of my queue is full, then I return a false. That's how I put it in Python here. Then if I am removing an element, I take again the global full queue length and the upper bound again with the value of, I might not need to take the upper bound because we already have that. So we're saying now if the queue length is bigger than 0, it means that there is something to remove. And the value that I want to remove is the one that is sitting on front pointer. And I have to replace, remember the logic that I told you when we were doing the pseudocodes part. When I want to remove an element, I would just take the element that is on the front pointer. Then I replace it with none. I now go ahead, I now want to change the value of the front pointer now. The front pointer will change based on two things. If it is already equal to the upper bound, then I change it to be the first index position in the queue, which is position number 0. But if it is less than, it means that I'm just going to be incrementing the front pointer. If it is less than the upper bound, I just increment the front pointer plus by 1 to get the value that I wanted. So at the very end of the day, to indicate the next free, the next front pointer, then the value of my the number of elements in my queue are supposed to be reducing by 1. So queue length minus is equal to 1, just the same as queue length is equal to queue length minus 1. Then I print out the value that I just removed. Then I go ahead and return true. Then else I'll print that the queue is empty. There is nothing to remove. So I might need to run this to test this so that you can just run it on your own. So let's have it. So if I am to print my queue like this, my queue has got 4 elements that are none. So if I want to enqueue, so if I enqueue, let's say 34 like this, if I then, it's returning true. If I print my queue, it's telling me that I've added an element. If I again take probably enqueuing 45, okay, 45 like that, it's still telling me that's true. Then if I check, I have my queue coming through to be 45 like that with another element. So let me enqueue a couple of elements. This, I enqueue again, maybe this, that's still true. Let me add now, okay. If I check my value of my queue has got those 4 elements. If I want to add again another element, let's say 0 now. Let's say 1, 1. It's going to be coming through to give me what? The queue is full. So what do I have to do? I have to dequeue. So if I dequeue, I will remove 34, which was the element that was first added. And what is my queue looking like now? It's now looking like this. This is now an empty space. So if I'm going to be enqueuing now, enqueuing, let me add 100. 100 is going to be coming on that very first part. See that? But if I dequeue, 100 was the last added. 45 is the one that is supposed to be getting out now. So if I say dequeue now, come on. If I say dequeue now, I'm supposed to be seeing 45 being printed out. Then to see how my list is looking like, it's looking just as is supposed to be looking like, right? So basically that's how a circular queue is going to be working. You can just go through the video again, take the code and type it on your own so as to get the full appreciation of what we just did. Yeah, that's pretty much it. If you have any question, please feel free to reach out to me so that we can actually just discuss more about it.